All right, we're continuing with section 10.6. Let's have a look at another example. The half-life of caffeine in a person's bloodstream is about 6 hours. If a person's bloodstream contains 80 milligrams of caffeine, then how much of that caffeine will remain after 14 hours? So in the previous page we did a half-life problem. In that one they were talking about the amount of the substance being measured in percent. Here with the caffeine they're doing it in milligrams. So we have to pay attention to that difference, but other than that it's going to be a very similar problem. So what we want to do is start out by making a chart, and we'll think about our inputs and outputs. So we'll have time be our input, and we'll use f of t for our output, and that will represent the amount of caffeine. So what we always want to do is put a 0, and then we want to put the half-life, which would be 6 hours. And then sometimes it's interesting to maybe add the half-life a couple more times, so maybe 12 and 18 as well. For the 0, we want to put however much caffeine was in our system when we started this process, and they're talking about us starting off with 80 milligrams of caffeine, so that's what we'll put in. And then we just have to remember that the half-life is the amount of time it takes for half of that to go away. So 6 hours later, that should drop from 80 milligrams down to 40. I think it's a good idea also, at least on one of these, to put the units just to remind ourselves that we're doing milligrams this time instead of percentages. And then that's enough really to get the equation, but I think it's good just to think about this a little bit more in terms of what the half-life does. It's not that we lose 40 milligrams every 6 hours, it's that we lose half. So 6 hours later when it's 12 hours, this won't drop down to 0, this 40 will get cut in half and it'll be 20. And then 6 hours later it'll get cut in half again, so that would be 10. So there's a table of information that we can use to try and come up with our equation, and what we'll want to do is use exponential regression, which is always what we use for half-life problems, is exponential. So we'll put those times in L1, and we'll put those amounts of milligrams into L2, and then we'll do the regression and write our equation. So let's bring the calculator in, and let's hit stat and edit, and then we'll enter in those times, so 0, 6, 12, and 18. Go over to list 2 and enter the milligrams, so 80, 40, 20, and 10. Once we get our data in, we can hit stat, go over to calc, and linear regression is what we used to use, and we still would if it was linear. This time we're dealing with something exponential, so we're going to choose the exponential regression. And then our data is in L1, comma L2. So we'll do that and we'll press enter, and we get our A and our B. Notice that A matches our y-intercept, which should be 0A. Notice that because this is theoretical data, it should be perfect, and we're getting r squared of 1. Your calculator might not show that, but if it does, it should be 1. Alright, so let's go ahead and write that equation down. So go ahead and note the pieces here. A was 80, and then B, they didn't tell us how many decimals to put, so we're going to round it. Rounding brings in error. So I'm going to go ahead and just put several. So 890. Let's go ahead and just go with the 9. That should be okay. I think we're using 4 significant figures there, and we just have a couple figures over here, so that should be all right. And then f of t would be a times b to the t, so that would be 80 times 0.8909 raised to the t. So we've got an equation, and now we just want to use that to try and answer the question. So how much of that caffeine will be in their system after 14 hours? So when they give us the 14 hours, they're telling us t equals 14. Because of our chart, we have a decent guess. After 12 hours, it'll be 20 milligrams. After 18, it'll be 10 milligrams. So the answer to this should end up being somewhere between 20 and 10. And we can figure out that answer by doing f of 14. So that's going to be 80 times 0.8909 raised to the 14th power. And then we'll just round that to 1 decimal. There's no rounding directions here, so we'll just do something reasonable. All right, so let's see, 80 times 0.8909 raised to the 14th. Just a quick thing to point out, the parentheses here are just kind of visual to separate the exponent from the number and from the multiplication. They don't have to be there on the calculator. You can put them in if you want, but you don't have to. So 15.9. And then again, we want to remember what units we were measuring in. So this is a value of F, so it would be over here, and that was measured in milligrams. So 15.9 milligrams of caffeine should still be in the person's system after 14 hours. All right, so there's another Half-Life example. You just want to make sure that you remember to think about what units you're measuring in. Sometimes it's percent, sometimes it's milligrams, and it could be other things as well. So just always be careful and make a note of what you're doing. All right, so moving on to the next example. Sales of fish oils grew exponentially from 30 million in 1995 to 627 million in 2007. Predict the sales of fish oils in 2014. All right, so this one is not a Half-Life problem, but it'll be similar in the sense that we're going to do regression because it looks like they've given us two ordered pairs. In 1995, we had 30 million. And in 2007, we had 627 million in sales. So those look like ordered pairs. I guess we could use the year, but it's more common to set a starting point for t. We might as well do that with the lower year. So the first thing I'm going to do is say, let's let t equal the number of years since 1995. All right, so now we'll make our chart just like we did last time. So t and f of t, and 1995, actually let's add the year onto our chart as well. So for the years we have 1995, and then we also have 2007. And we started the clock here in 1995, so that's year 0, 2007, subtract the 1995 away, that would be 12 years later. And then in 1995 it was 30 million, and in 2007 it was 627 million. So we've got a little chart just like we did on the problem up above. So we can take that data and put it into our calculator as L1 and L2. This should turn out to be A because it's 0A, but the calculator will help us sort out the B. We could do it by hand as well, but the calculator is really convenient for this sort of stuff, so we'll take advantage of it. So go in there, stat, and edit. We have that old data from the Half-Life problem, so we'll clear that out. Enter in the new data, 0 and 12 for the inputs, and then 30 and 627 for the outputs, and then stat, calc, all the way down to exponential regression, and our data is in L1, comma, L2. All right, so A is 30, and B is approximately 1.2883. So I'm doing 5 significant figures there. That should get us a decent answer. Notice here they have 3 significant figures. I always like to have more significant figures in my base than what they're using for their outputs, so that way I can get accurate outputs. All right, so f of t is approximately 30 times 1.2883 raised to the t power. And then let's think about what it is they want us to answer. So they said predict the sales of fish oils in 2014. So the t for that would be 2014 minus the starting year of 1995. So that should be 19 if I'm doing the subtraction right. That's also 7 years later than this, which would be 12 plus 7 is 19. So a couple ways to think about that. And then our prediction would be f of 19, which would be 30 times 1.2883 raised to the 19th power. And I'll just put 1 decimal place on there and go to the 10th of a million. I like to do typically 1 decimal place more than their original data values were given to. Of course, if we're in my math lab, we just need to pay attention to what it is they're asking us for and go with that. All right, so 30 times 1.2883 raised to the 19th power. So 3, 6, 693.55, so this would be a 6. And then that would be millions of dollars. And to me, there's just something a little weird about talking about 3,693 million. If we're going to do that, either we should multiply by a million, and that would move the decimal 6 places to the right. So 3,693,6 with all these zeros. So this would be the millions place. We have 3,693 million. When we write it that way, we can also see that this is 3,693,000,000. So we could also write that it's something like approximately $3.7 billion. So we have some choices in how we could write it. This one to me is the most awkward one, where you're talking about how many millions and yet you're really in the billions. So that's a little strange. But really what you have to do is pay attention to what my math lab asked you for. Does it want millions, billions, or just dollars? And then you have to be ready to adjust to whichever format they're looking for. And just one other thing to point out. We want to get in the habit of thinking about the rate of growth. They didn't ask it here, but I'll just kind of throw that in as a bonus. If you look at how much we are above 1, that would be our growth rate. So that 0.2883 is about 28.83% growth per year. And we want to get in the habit of noting that if we have a base that's above 1, then that represents growth, and the amount it's above 1 represents how much growth there is. All right. Okay, next example. Percentages of adults surveyed who plan to attend a Halloween party this year are shown in the table for various age groups. Let's let P, which will be f of t in function notation, be the percentage of adults at age t years old who plan to attend a Halloween party this year. So we've got people in age groups, and then we have a percentage for those groups. But as we've talked about before, you can't really put an age group into the calculator to do regression. So what we're going to want to do is take this representative, which is kind of in the middle of each age group, and let that be our input. So that's going to be L1. It's also going to be our variable t. And this will be our percentage, or our values of f of t. And we'll put those into L2. So let's see, they say to find a linear equation and an exponential equation for this function. So we are going to do that, but I want to kind of explore that a little bit. So let's go ahead and enter the data in, and then we'll see about what they're asking there. So first thing would be to go to stat and edit and put these into L1. And then put those percentages into L2. And then they ask us just to jump in, do a linear equation, do an exponential equation. But if we're going to use the graphing calculator, then it makes sense to me that we should do a plot first and look at what makes more sense to model this data, linear or exponential. They're going to have us answer some questions that help us get at that, but really the best way to decide whether you should have a linear or an exponential model is to look at the pattern in the data. So I'm going to go to the y equals, and it looks like I have some old things there, so I'm going to clear those out. My plot is turned off, so I want to turn that plot on. That should be set up to be a scatter plot. And then I just want to make sure the window is right for this. So if my ages go from 21 to 70, then maybe I could go something like 20 to 75 and count in fives, a little smaller and a little bigger than this. Maybe give ourselves a little bit more room on the small end and start at 15. There's no specific right or wrong answer there. You do want to make sure all this data fits in your range. On the percentages, we're going from 6 to 44. Because the 6 is so close to 0 compared to 44, I think we should just start at 0. And the max is 44. How about if we just go up to 50? And we could number in fives there as well. And that seems like that should fit the data pretty well. So let me hit graph and have a look. This is kind of a close call in a way between linear and exponential. The linear looks like it would do a good job through here, but then the exponential might be better because it seems like it's starting to flatten out as we get to those older ages. So they both actually seem reasonable. So we're going to go ahead and do the two regressions like they just asked and find those equations, but we'll graph both of them too and think about which one's a better fit. So let's see, let's do the linear one first. So stat, calc, and I'm going to go to linear regression, and then I'm going to hit some extra keys here to do the storing of this. So let me show you that as I go through. So linear regression, ax plus b, and then my data is in L1 and L2. And then I want to store that in y1. So I'm going to hit the variables key right here. I want to go to y variables, and it's a function that I'm doing, and then so y1. So this will give me the regression equation, and it will also store that at the same time. All right, so let's write those two down. I'll give myself a little bit more space here. So the linear one, They did say to use f of t, so I guess we have to use the same thing both times. So we'll do f of t, and we'll say that one is approximately, let's see, ax plus b, so negative 0.78758 times x, or in this case our input is t, plus b, which is 57.4766, let's say. No rounding rules given, so I'm just trying to do somewhat a lot so that I get accurate predictions. And then for the exponential regression, very similar process. So we're going to go stat, calc, and we're going to drop down to exponential regression. We're going to do L1 comma L2 again, and we're going to store it again. This time we don't want to store it in Y1 because that would go over the top of our last one, so I'm going to do variables, y variables, function, and I'm going to store it in L2 this time. So it's a little bit extra to do that, but it does get the equation stored without us having to do it. So a times b raised to the x, so a is 113.0439, and that's times the base, 0.959562 raised to the t. So I've got both the linear and the exponential forms of the function, but I've also stored them. So if I hit y equals, I see both of those equations there, and I didn't have to type them. That's one benefit. The other benefit is it put all the decimals that it had in memory, so you get super accurate versions of those equations entered in. And then if we hit graph, we'll see the linear one. That's a decent fit, but it just looks like exponential's getting a little closer and makes more sense with the way the data is curving there. So if I had to choose just based off the picture, I think I'd go with exponential, but we have both of them ready, and they both do a reasonably good job of fitting the data. All right, so let's see what they have for us next. For ages of adults over 80 years, which of the two models likely gives the best estimate of the percentage of adults who plan to attend a Halloween party this year? So this is a question designed to get at what's the better model, linear or exponential. What I don't like about this system is we're focusing too much on just one age group, 80-year-olds. And as 80-year-olds, is that the most important age for Halloween parties? Doesn't really seem like it to me. But if we look at 80-year-olds, what we'll see is a problem with one model and that the other model seems reasonable. But I think really what you want to do when you're deciding which model's better is look at overall, not focus on a specific age. But they asked us to, so let's go for it. If we hit trace, and we use the up and down arrows to change the function, this negative 0.7871, that's the linear one. I want to plug in 80 to that, but actually I just realized I don't think I can do that because we didn't set up our window for that. So let me just change the window. Yeah, we had a max of 75, so let's just go a little higher. Let's go to 95. And because of something that's going to happen on this question they ask us, I'm going to give some room for a negative as well. Even though you can't really get a negative percentage, I'm going to change my y min to negative 10. So we'll graph again, so we'll let it draw. And I think you can see the problem already with linear. Somewhere around this age, whatever it is, the linear model starts to go negative, which doesn't make sense. And so that's really kind of why they're asking us to do that. So let's go ahead and look at what happens. So if we do trace and we jump onto the line, while you're in trace mode, if you just type a number like 80 and press enter, it'll make a prediction. So the line is saying that for 80-year-olds, you get negative 5.5% going to Halloween parties. That doesn't make any sense. If we jump onto the exponential model, the 113 model, and while we're tracing on that, if we type the 80, then we get 4.16. So that seems to make more sense, that the percentage would be low for 80-year-olds, but it still wouldn't be negative. So about 4.2%. So which of the models does a better job there? Well, here's our two predictions, right? So for the line, we get something that doesn't make sense. But for exponential, I think we get a reasonable answer. So I guess you could argue then that the model is breaking down sooner for the line than for exponential. I still think which one you use should be based on how well it fits the data and not focus too much on 80-year-olds when that might not be the people that you really want to talk the most about when you're doing Halloween party discussions. So, but it does seem to still indicate the same as the graph that exponential is probably the better choice. All right, let's go ahead and look at the next one. What is the base of the exponential model and what does it mean in this situation? So the base of the exponential model, let's pull this down a little bit, is right there. Roughly, let's just call that 0.9596. We'll just shorten it a little bit. So what does that mean in this situation? Well, first of all, the base is smaller than 1. That means we have decay. And that makes sense based on the graph too, right? We have a decrease in percentage of people going to the Halloween party as the age group gets higher. But then if you want to be more specific, you want to know how far below 1 is that. So you look at 1 minus the base, and you can do this on your calculator. It should come out to be 0.0404. And then think of that as a percentage. So move that decimal over a couple spots. And then you could say that's 4.04%. And what you're seeing there is the decay rate. So for every additional year of age, because that's what the T represented, was how old the people were, the model predicts that 4.04% less people will go to the party. And specifically to Halloween parties. So every year that goes by, there's about 4% less going to the party compared to the previous year. We're not talking about a subtraction there. So we're not saying that this is dropping by 4% for every year of age. It's 4% of what it was the previous year. And you got to be a little careful here. This isn't 1 year going by. That's 10, 10.5. But the base is always telling you what would happen for every additional 1 year of age. So every year about 4% less people than had gone the previous year. So if you knew how many people went the previous year, you multiplied that by 4.04%, you'd expect about that many to drop out of the Halloween party going idea or spirit, if you will. All right. Okay, a couple more questions with the Halloween party problem. Use the exponential model to find f of 26, and what does it mean in this situation? So first we can just find it, f of 26. There's two ways we could do it. I've already showed you how to use the trace method to plug in. like I did with the 80-year-olds. So I'm going to go ahead and bring that back our equation and show you how to do it by hand as well. So if you want to do f of 26, you could say that's 113.0439 times 0.959562 raised to the 26. And then we could just enter that in the calculator. So I'll go ahead and do that. So 113.0439 times 0.959562 raised to the 26th power. And let's see, that would be about 38.65. Now I started to think about what are the units on there, but I kind of hesitated because they said to just find it first and then explain what it means second. For me, that's kind of always simultaneous. I'm always thinking about what does this mean and what does that mean. Here they just kind of broke it up first. Compute it first, then think about what it means. So this input was t, so that would be 26-year-olds. This is our output, which on this problem was percentage. So I would say that 38.65% of 26-year-olds attend Halloween parties. All right, let's look at the last part. Use the exponential model to estimate the number of 42-year-olds who plan to attend a Halloween party. Assume that there are about 4.6 million 42-year-olds. All right, this is just a small twist on what they asked above. The first thing I would do is get the percentage by doing f of 42. And that would be 113.0439 times 0.959562 raised to the 42nd power. So I'm just going to bring that in. It's so similar to the last one, I'm just going to hit second and enter and change that 26 to a 42 and save myself some typing. And I get about 19.97. And again, that is a percentage. And so the reason that's not the end is because they didn't ask what the percentage was. They said, where is it? Estimate the number, not the percentage, but the number. So we know it's this percent, and then we know there's 4.6 million people in that age group. So what we need to do is take 19.97% of 4.6 million. And so we would do that by doing 0.1997 times 4.6 million. And I'll do that multiplication on the calculator. That's 0.1997 times 4.6. And we get about 0.919 million. And now we're in that situation that I think is a little weird, where we're talking about it in millions, but we have less than a million. So I would say by multiplying by a million, that's 919,000 people roughly. And actually, instead of people, be more specific, it's 42-year-olds that we're talking about. So I would estimate that somewhere around 919,000 42-year-olds would attend a Halloween party, based on this fact that there was 4.6 million 42-year-olds at the time. All right, so one of the things they asked us to do on this problem was to interpret the base. So let's go ahead and think about that in general. So here's the meaning of the base of an exponential model. If f of t equals a times b raised to the t, where a is greater than 0, if that models a quantity at time t, then the percent rate of change is constant, and in particular, if the base is greater than 1, then the quantity is growing exponentially, and the rate of growth is the difference between the base and 1. And because the base is bigger than 1 and you want this rate to be a positive number, you do the base minus 1, and that would be the percent in decimal form. And then if the base is between 0 and 1, and really kind of focusing on the less than 1 part, you're going to get decay. And so you want to see the difference between your base and 1, and 1 is the bigger number, so do 1 minus the base, and that would be the percent in decimal form per unit time of the decay rate. So just showing you how this fits with the example that we just did. Right, our base was less than 1, so we knew we had decay. And then we looked at the difference between 1 and our base, and that in decimal form became the percentage that we had as our rate of change per unit time, which was for each year or per year. And we definitely want to get in the habit of being able to look at that base and quickly know, is this growth or is it decay, and what is the rate of growth or decay, and to be able to interpret that. The costs of 30-second ad slots during the Super Bowl have increased greatly, even when adjusted for inflation. Let C be the cost in millions of dollars of a 30-second ad slot at T years since 1960. And then they've listed some different Super Bowl numbers with the Super Bowl year and the cost in millions of dollars for the ads. So they want us to find the linear regression function and call that L, and the exponential regression function and call that E for this data set. Before I find either of those, I'd like to plot the data with a scattergram and see whether it looks like the linear regression is a better idea or the exponential regression is a better idea. So the first step in doing that would be to take these years and convert them to values of t. And t is the number of years since 1960, so we'll be subtracting 1960 from all of these. In 1971 that had been 11 years, 16 years, 21, and so on. When you switch to a new century, that can be a little confusing, but just do your subtraction over again. 2000 minus 1960 would be 40, so 2006 minus 1960 would be 46, and then this one would be 49. So now that I've figured out the values of t, I'm going to want to take those and put them into L1, and then these costs I'm going to want to put into L2, and that way I can make a scatter plot on the graphing calculator and have a look at the pattern. So I'm going to go ahead and turn that on. I want to go to the Stat menu and choose Edit, enter in those values of t. And then move over to L2 and enter the cost of the ads. And then I want to do a scatter plot. But before I do a scatter plot, I want to make sure my window is correct. So I'm going to go to the window settings. Right now it's set for -10 to 10, but my input values go from 11 to 49. So it might be more appropriate to go from like 0 to 60. It's a little below this and above that, giving 10 years about, roughly, on each side. And then I could number in maybe 5-year increments. For the outputs, the y values, 0 would be a minimum, and the max is 3.0, so maybe go up to like 3.5. Sorry, I'll get that minimum back at 0, and the max at 3.5. And then for the scale, maybe every $500,000, we could make a tick mark. So now I think the scale will display the data. Now I just want to make sure the data is set up, so I hit the y equals menu, and I notice that my plot 1 is not highlighted, so that nothing's going to graph right now. So I'll use the up arrow, press enter. That'll highlight that, so that plot will graph now, and I always have that one set up to be a scatter for L1 and L2. So if I hit graph, I should see the data displayed. And both a linear and a exponential seem like they would be a decent fit. I could imagine drawing a line through there that gets pretty close to those points. On the other hand, I do see a little bit of a bending pattern to that. And if I really think it's bending or curving, then probably the exponential will be the better fit. So at the moment, that's kind of my hunch, is that exponential will work better than linear. In any case, they want me to do both. So I'll start off with the linear regression function. So stat, calc, linear regression, number 4, and my data is in L1, comma, L2. So it looks like for the linear regression, we get a slope of 0.069349 and so on, and the intercept is -0.8378. Alright, so let me write those down. So for the linear function, I'll write L of t is equal to mt plus b, or at plus b, so 0.0693495 times t minus the intercept 0.8378 928. I didn't see anything here about rounding rules for how many decimals they wanted, so I just put a lot. Better to have too many than too few. When you're on My Math Lab, make sure you just follow the rules for what they want you to put there. So that's linear regression like we did back in chapter 5. Now let's try an exponential regression and see what we get for that one. So same idea. I'm going to hit the Stat button. I'm going to go to Calc, but this time I'm going to go down further and I'm going to find the exponential regression, which is down here at number 0. So highlight that, press Enter, do second L1, comma second L2, and it's going to give me a y equals a times b to the x, and it's telling me the a and the b. So I want to write those down. So the exponential function, e of t, would be 0.140625 times the base 1.064929 raised to the t. And I wrote a 9 there because that was an 8 followed by a 6. So that's using linear regression and exponential regression to come up with the equations, and that's what they asked us to do, right? Find the linear regression equation, find the exponential regression equation. And then they're going to start asking us to make some predictions. But to me, it makes sense that if I want to make predictions, first I'd look at those with the data and see which one fits better. So let me go ahead and show you how that works. So I'm going to bring the calculator back in, and I'm going to enter these two functions into the y1 and y2 area so that I can see their graphs with the data. So y equals, for y1 I'll enter this one, 0.0693495 times t, or the x button on the calculator, minus 0.837828. So there's one function, the linear one, and now the exponential, 0.140625 times 1.064929 raised to the t, or I'll use the x key. Just a quick comment, there's parentheses here that I didn't put in the calculator. When you only have a single number in parentheses, they're actually optional. Here they're just kind of visual to help us separate that number out from the t and cause a clear visual break. So as we hit graph, we'll see our data, and then here comes the line, decent fit, and here comes the exponential, and because it's curving, it can follow along that pattern of the data, and I would say that it seems like that one is coming closer to the data values overall. So when it comes time to make predictions, in general I would say I'd rather go with this exponential one for this data set than the linear one, because it's coming closer to more of the data I see, so it probably would do a better job of predicting the data that I can't see as well. Alright, so let's go ahead and start doing that job. So let's read part B and see what they want from us. Use L, your linear function, and E, your exponential function, to estimate the cost of a 30-second ad slot during Super Bowl I, which was in 1967. The actual cost, adjusted for inflation, was $200,000. So which function did the best job of modeling the situation in 1967? Well, if you take 1967 and you subtract away the 1960, which was our starting point, then you get t equals 7. So we want to plug that into both of the two functions. So looking at this one, we want to put the 7 in here and therefore also there. So L of 7 would be equal to 0.0693495 times 7 minus 0.837828. And then I also want to do the same thing for the exponential function. I want to plug the 7 in here, and so then also as the exponent right there. So E of 7 would be 0.140625 times the base of 1.064929 raised to the t, which is going to be 7 for this particular problem. Alright, so we'll bring in the calculator now, and we'll see what we get for each of those two. So I'm going to hit second quick, get back to the calculation screen for the linear one, 0.0693495 times 7 minus 0.837828, and I get a negative, which is interesting. Just a little strange, right? So I'm just going to double check that I put that in right. 693495 times 7 minus 0.837. It looks like that's correct, though it can't possibly be correct for the situation. Does it say how to round it? No, so I'm just going to put a lot of digits there, negative 0.3523815. I'll just put everything I see. And then let's see what we get for the exponential one. So for that one, we have our base of 0.14, sorry, our multiplier out front, 0.140625 times our base, 1.064929 raised to the 7th. And for that one, I get approximately 0.218427. So I think putting 6 decimals is actually ideal for this because these are in millions of dollars. So if we take L of 7 and we multiply that times a million, that would move the decimal over 1, 2, 3, 4, 5, 6 spots. And I'll go ahead and round to that nearest dollar, so I'll make that 1 round up to a 2. So I'm going to guess for the linear one, negative $352,382. And for the exponential one, that would become, move the decimal over 6 spots when you multiply by a million, so 1, 2, 3, 4, 5, 6. That's going to be $218,427. So the linear equation is predicting that an ad for the first Super Bowl didn't actually cost you money, that you were paid $352,382 to put an ad on. Of course, that makes sense. Nobody's going to pay you to put your ad on. We skip commercials. We don't pay to see them, right? So that seems like a bad prediction to me. And yet this $218,000 is very close to the $200,000. So what I think they want us to get out of this little experience is to see that because the exponential function fit the data better, and let's bring the graph back in, right? Because it fit the data better, you'd expect better predictions. And we can also kind of see what's going on. Why do we get a negative? Well, look, the line disappears below the x-axis, so it becomes negative right about there. And 1967, I think we might have used a scale of 5. So 1967 would have been like, I think, right around in here, which is a negative zone. But of course, it doesn't make sense. And if you look at the pattern of the data, it looks like it's curving this way, not going down. So getting this 218,000 seems like a better plan to go with that curved graph rather than the straight one. Not just because it's closer to the right answer, but because it follows the data pattern more overall. So their strategy with these questions seems to be pick a point, show that one function works better than the other, and therefore exponential is better. I actually would disagree with that. I think that the exponential is better because it fits the overall pattern of the data better. I'm not going to focus on just 1967 and see which one does a better job. I want to look at the whole data set and see which one does a better job. And when you do that, it definitely seems to me like the exponential fits better. So they do this just to kind of confirm that for us, but for me it's more of a visual thing. Look at the data, does it look more straight or curved, and then do your two equations and graph them, and then which one seems to get closer to the points. It seems to me like the exponential one is better, a better fit, and so when they ask me to make predictions, I'd want to make them with the exponential. I would trust that one more. Alright, so continuing on with that problem, let's look at part C. Find the slope of graph L and the base of E and describe what they mean in the situation. So we have these two different kinds of models, one for a linear pattern, one for an exponential pattern, but then the numbers we get from those also get interpreted in different ways. So let me bring in that previous page so we can look at those two functions. So for the linear one, the slope would be the coefficient of t. Let me just put an L here. So the slope would be the change in output, which was really cost. So I'm going to put change in cost over change in input, which would be our t. And then that was 0.06939495 over 1. Then what are the units on that? Since it's cost, it would be dollars, right? Except for that it says in the table that it's actually millions of dollars. So I'll multiply by $1 million. And then the t was time measured in years, so I'll put a year. When I multiply by the million, the decimal is going to move over 6 places. So that goes over 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right there after the 9. So that would be $69,349 and I guess 50 cents if we want to keep that 0.5 over 1 year. So what is that telling us? For each additional year that goes by, the cost of a Super Bowl commercial is increasing by about $69,349.50. So let's go ahead and squeeze that in here. So for each year that passes, the cost of a Super Bowl commercial, here space is at a premium, so we'll say a Super Bowl ad like they did, increases by how much? By $69,349.50. Alright, so that's L. That's the one that we're used to doing. Now the new one would be for an exponential function. So for E, we're going to focus on the base, and the base is 1.064929, and that's what we're multiplying by every year. And remember, if you multiply by 1.0649, doing 1.0649 times is the same as doing 106.49% of, and this part above 1 tells you what percent increase you're getting, but it's telling it to you in decimal form. So when I see that, I would ignore the 1, move the decimal over a couple spots, and get 6.49. That's probably enough decimals, and that would be a percentage, and it's the percent that the output, which is cost, is increasing each year. So rather than saying that the commercials go up by a fixed amount each year, 69,000, I'm going to put it into a percentage term when I look at the exponential and say each year the cost of a Super Bowl ad increases by 6.49% compared to that previous year. So when you do linear, you're saying you get a constant rate of growth. Every year it goes up about $69,000. But with exponential, you're saying it's a constant percentage. But a constant percentage is not constant growth because it's of the previous year. So as the cost goes up each year, the 6.49 gets applied to that higher number, and we get a higher increase each year. So when things are growing exponentially at a percentage rate, you'll get this bend. When things are growing at a constant rate, like in a linear one, you'll get the straight line. So those are the two different interpretations that they wanted us to give. Alright, so now at this point, we're going to finish off with a couple more, and you're going to see that they finally are kind of on board with us that the better one to make predictions with is E, and so they're going to ask us to use E for both of these last ones. Alright. So let's read through part D. In Super Bowl, let's see, Roman numerals, that would be 36. In 2002, a 30-second ad cost $1.9 million, and that was the first decline in cost. Use E to help estimate the total loss in revenue from ad slots during Super Bowl 36, which was likely due to a poor economy that year. So they're telling us how much it really cost, but they're saying, look, we're probably going to get better estimates of what it should have been from the E function, so let's use that to make our estimate. 2002 is 42 years since 1960, so that would be E of 42. And we'd want to plug that into our exponential function. Let's just bring that in real quick. So that'd be 0.140625 times 1.064929 raised to the 42nd power. So let's see what the calculator says that would be. So 0.140625 times 1.064929 raised to the 42nd. And this is in millions of dollars. I get 1.9748311, 1, 2, 3, 4, 5, 6. That would allow us to go to the nearest dollar, and that is in millions, right? So it's dollars, but millions of dollars. Okay, so the actual value of that ad was $1.9 million, and our estimate was this 1.97. So they wanted to see how much revenue was lost. So we would have expected $1.97 million, and they actually got, let's add another digit there, $1.974 million. I guess that would be a 5 because of the 8. And they actually got $1 million, or $1.9 million in revenue. And if we subtract those two, that tells us the difference between what we would have expected based on our equation and what actually happened. So you can see those 1.9s are going to cancel. So you'd be left with 0.075, and that would be millions of dollars. I think it's weird to talk about a decimal amount of millions. So if we move that decimal over 3 spots, or actually just multiply by $1 million, then we'd move it over 6 spots, those 3 and then 3 more, which would be zeros, then we would get $75,000. So it looks like they sold those ads for $75,000 less than they would have expected, and so every 30 seconds that poor economy, I guess, was costing them about $75,000. So I'm just showing you those steps again. If we do the 1.974831, we subtract the 1.9. That shows us the difference, and that was in millions. So times 1, 1, 2, 3, 1, 2, 3. So 6 zeros for a million, and then we get $74,831, or if I round it off, $75,000. All right, and then finally, they want us to use E to predict the cost of a 30-second ad slot during Super Bowl, oh my goodness, my Roman numerals. I think this is 40 and then plus 8, so Super Bowl 48 in 2014. So how much should an ad have cost during that Super Bowl? So first of all, we'd figure out T. T is 2014 minus the starting time of 1960. So that's 54 years later. I think, what did I say that was? Super Bowl 48. Earlier they said the first Super Bowl was 1967, so there's some hope my Roman numerals were right there. And then how much would we expect the ad to cost in that year? That would be E of 54. So that'd be 0.140625 times the base of 1.064929 raised to that power of 54. And they're asking us to use E, and I would want to use E because it looks like the better fit to the data. So let's see what we get out of that. So 0.140625 times 1.064929 raised to the 54th power, and we get 4.201, and that would be millions of dollars. So if I multiply by 1,000,000, I get $4,201,243. So it kind of went back and forth on my decimals here. If you just left it like this, you could say that it's about 4,201,000. If I use the original number from the calculator, I can go to the dollars place. What you should do when you're working on the homework is see what the rounding directions are from my math lab and then follow those. So $4 million for a 30-second ad, and then think about how many of those ads you actually end up seeing during the Super Bowl. So they are bringing in a lot of money from those Super Bowl commercials. All right, so here's the 4-step modeling process. If you want to find a model and make estimates and predictions, create a scattergram of the data and decide whether a line, a parabola, an exponential curve, or none of these comes close to the plot. So we didn't cover parabolas, so that would be one that we would leave out. We're looking to see, does it look linear or does it look like it's curving, and then we would go with exponential. And notice that even though they didn't ask us to do a scatter plot for this problem, they are suggesting in general you should do that. So even though they didn't ask, I did one because I want to have a look at which one looks like a better fit. Find the equation of your model. They had us find the equation of both the linear and the exponential for this one. I would argue that the reason you look at the graph is just so that you can pick which one would be better and just go with that. It is pretty easy to do on the calculator, so no harm in doing both and then graphing them both and seeing which one fits better, and then write that equation down. And then verify that your equation has a graph that comes close to the points in the scattergram. If it doesn't, check for calculations errors and so on. So I would argue that this step 3 is actually kind of happening before this, that we would want to graph those equations, both of them, the linear and the exponential, and then see which one fits better, and then write our equation down. And then use your equation to draw conclusions, make estimates and or predictions, interpretations of growth rates, like using the slope or the base, stuff like that. All right, that wraps up section 10.5.